Fuses actually sort of kind of fall into three groups. I mean, it's very common to see the little glass ones. The higher fuse ratings, we see them a little bit more substantial, big brass plugs or copper bars. So, 50 amps and above, below 50 amps all the way down to milliamps. These guys typically are going to be about 40, maybe occasionally you'll see a 50 or 60 amp one, although they'll be built a little bit differently. They're a little bit bigger. These automotive type or GM type were originally developed. They typically come in 5-unit increments: 1 amp, 5 amps, 10 amps, 15, 20, etc. They say you can tell they're blown by looking at the end of it, but I usually have to pull them out and look, and you can sort of see that one's good, and this one, the end is blown off. I've also had the pleasure, more than once, of having a fuse, make that go away. Something like that in there that looks perfectly good. Absolutely looks perfectly good until you pop it out of there and measure with an ohm meter and you realize somehow one end or the other broke off and it's no longer providing the conductivity. Most of the time though, when they blow with some force and the inside gets pretty smoked and fried. This one here is a special type of fuse designed to control the rate at which it blows, either fast blow or slow blow.
Will those automotive ones be in an airplane?
I've actually started to see some installations where you buy a component and an inline version of one of those is in it. So it's rare though, but so this is what happens when the circuit breaker doesn't work. So in any given circuit, and this is going to change within the circuit. So within any given portion of the circuit, the expected loads on it cannot exceed that branch current carrying capacity. So for example, if you look at the wiring diagram right there, they sort of show all the lines kind of being the same size. But this guy right here is 1,000 kilovolt amps. In through here, 1,600 kilovolt amps. And then this is going to be a big heavy duty bus. These are going to be a little bit smaller coming out to individual circuit panels. Then the wire is going to get smaller and smaller. But then within here, this wire has to be able to handle everything that comes off of that. Just like this wire has to be able to handle everything that comes off of that, etc. So if you have multiple levels of circuit protection like we do in this building, then you might find yourself having different ratings. So, for example, let's say I have that avionics bus. Now, if that avionics bus is right adjacent to my regular bus, I might just have a switch between them. But if the distance between the two is substantial, I might actually put a circuit protection between them too. In which case, all the avionics components might add up to 50 amps worth of load. So I'm going to make the circuit to be able to handle 50 amps of load, and the circuit protection would be able to blow the circuit breaker before this kind of damage can occur. Even though all of the users coming off the avionics bus might be 8 amps, 10 amps, 5 amps, 3 amps, whatever. So, another way of saying this is the circuit protection is designed to protect the circuit. So it has to be designed to protect the that element or component of circuit that it serves. Which means if I design the circuit for 50 amps, the circuit breaker needs to blow at something below 50 amps, right? All right. Now, voltage rating as opposed to current rating really isn't a function of the wire itself. If you look at the inside, the secondary wire, the secondary coil of an ignition coil, like in your car that's putting out 100,000 volts, if you look at the wire, it's finer than your hair by quite a bit. It's a dinky little bitty wire. Doesn't need to be that big. It's not carrying current. However, what matters in that wire is the insulation. The insulation has to be able to stop 100,000 volts from jumping to another part of the circuit. So in most cases, because we operate in 12 volts or 24 volts, or maybe even a few cases slightly higher, we typically make all switches to be able to handle either 125 or 250 volts, except for very specialized ones, which are going to be operating at much higher voltage, 400 or 600 or something like that. So what we see in aviation, we're rarely going to see a switch that doesn't way over exceed the voltage capacity, or any other part of the circuit, the wires, other components. And then of course the obviously other factors, environmental factors, will affect how the circuit needs to be protected. So we kind of primarily, with respect to circuit carrying or circuit protection, the two big categories are fuse, which are one-shot deal. Once it's blown, you can only replace it, or a circuit breaker. And within the world of circuit breakers, in aviation, we typically have three different types. One type, like this one here, which clearly blew out part of its element, it's just a push button. So you push the button to reset it, and you can't unreset it. The only way to unreset it is to get too much current. Then it'll trip and unreset. The next kind are going to be like these. They're like the push button, but they have enough of a little collar that you can grab them and pop them out and turn them off. The last kind actually has a toggle switch, and it's meant to be both a circuit breaker and an on-off switch. Now, circuit breakers somewhat work like fuses do, in that they'll have some type of a heating element through which either all or part of the current will travel. And if the current exceeds a certain value, that heating element will get hot enough to cause a bimetallic plate to start flexing. And as it starts flexing, it pops or trips the latch that holds the switch together and causes this to pop back out. So in the case of current carrying, it's always going to be a function of the choice of the material, which for us sort of isn't a choice. We're always going to use copper. Okay, occasionally there's aluminum, but pretty much copper. But it's really cross-sectional area and the length of the run. And the length of the run really is about the allowable voltage drop. Okay, if I use a smaller wire, I'm going to have a greater voltage drop. Okay. So then, because we tend to get wires fairly hot, or because current traveling through a wire tends to promote heat, heat rejection can become an issue if the wire carries enough current compared to its cross-sectional area. I mean, if it's a little bitty milliamp type circuit running from LEDs or something, you're probably never ever going to get hot enough for it to be an issue. On the other hand, if it's a 10 amp radio during transmission time with a lot of transmission, then yeah, those power leads could get a little bit warm. In which case, if the wire is bundled or not, it's going to affect its ability to reject heat. And of course, we've got a 40P13 to use the correct wire size. So, once you have a sense of what the appropriate wire size is, and the total amount of current that's going to go on that circuit to determine the wire size, you then need to go back and say, all right, what kind of current protection do I need? And there you're going to be doing some looking in the charts and say, all right, this circuit cannot handle more than 8 amps. I'm going to overbuild it slightly. So let's say I have a total of 5 amp users. I'm going to build it to where it can handle 10 amps. And then I'm going to shoot for the middle. I'll say, let's use an 8 amp circuit breaker. That way, the circuit protection will pop out at 8 amps, which is above what the total load's going to be, but it's below what the melting point of the wire is going to be, right? Now, having said this, yes, you can use a variety of different things to look this up, 40P13, etc. Most of the time when you buy an airplane part, Cictronics, intercom, Garmin GPS, blah, blah, they list right there in the installation manual the wire sizes they expect you to use. That may or may not be FAA approved data, but it's better than any other. It's better than nothing. I think in most cases, if you bought a Garmin 1000 and use their recommendations, it's very unlikely that the FAA would ever come back and say, "Oh, you didn't do that right." Well, I did what the manufacturer said to do. In fact, really, the only place the FAA would have legitimate cause is if, by installing it, you exceeded the generating capacity of the generator, right? You got a doctor or a lawyer who just wants more and more and more whistles, more bells. Okay. So again, rely on the manufacturer's recommendations for wiring size and circuit protection. And you'll find if you look at them, they're way overkill. You'll read in the skin, okay, maximum is 0.72 amps, blah, blah, blah. And they say, use a number 18 wire with a 4 amp circuit breaker. That's way overkill. You'll never, ever, that component will never, ever generate enough current to trip that circuit breaker. So if the circuit breaker trips, probably because there was a short somewhere.
Isn't that just precaution?
Huh?
Isn't that just precaution on their
Oh, absolutely. Yeah, absolutely. But from your perspective, you're in a pretty good place at that point. They've said, say 4 amp, 18 gauge. Okay. I know that if I dead short that wire, circuit breaker is going to blow before it smokes. On the other hand, if I had a 26 gauge wire, that might not happen. And at the end of the day, I guess another way of saying this is, if you follow their recommendation and it's wrong, even though you did your best effort to say it's right, whoever is going to be suing is going to be way likely to go after Garmin than you. They'll name you in it, but Garmin's the one they're going to go after for putting out the wrong information. Okay, the other thing about circuit protection is you need to be conscious of what characteristics or what behavior the circuit protection enacts itself. So in some cases, you might have a situation where you get some transient. Every time I hit transmit on the radio, current value is going to go way up. So because of that, I might want a current protection that takes a little bit of time. And at the end of the day, remember we said even with the fuse, doesn't the fuse have to heat up before it blows?
Yeah.
So there's gonna be a finite amount of time, and that time is gonna change depending on how much current you're hitting it with. So this chart sort of shows trip area versus working area. And note they say, you know, at this low, 100% of its current rating, you've got 500 seconds or maybe even more, it's not gonna trip. But if I get up to about 300% of its current rating, it's gonna trip in 1 second. And if I start getting higher, 6, 7 times, it's gonna trip quite a bit quicker. Okay, and that's actually a fairly not slow response circuit breaker. Most of them are actually quite a bit quicker than that. What you would actually see is this being 500 milliseconds or half a second. Would be a more accurate description. So if you pull a fuse out and it looks kind of weird, go back and make sure you're looking at the right part number, because it might be a slow blow fuse, or it might be a specialized fuse that goes in there. Or same thing with the circuit breaker, it might be a specialized circuit breaker. Another way of saying this is most circuits, unless they're really, really fine wire, they can handle for a short period of time a big burst of current. And when I say short period, milliseconds, 10 milliseconds or 10,000th of a second. Yeah, you hit it with pretty high current very, very briefly. It's not going to have that time to get hot, is it? Because the heating takes a while. So now, on the other hand, a sudden surge in current or sudden surge in voltage and current can toast the load. They can make the little brain inside the magic box go, ouch, and stop working. That's okay. It's in a metal box. It's not going to catch on fire. Or at least the fire that it catches in there isn't going to come out. The wires outside, hopefully, will not have that happen to them. Now, one of the things that was sort of interesting about Swiss Air Flight 111, I think it was,